So, morning everyone. Thank you very much for showing up. I've actually been to MSK many times, but never as a lecturer, so I'm super excited. So, yeah. So, a bit about me. So, I'm a graduate student in the Material Science program at Columbia University, which is inside of the Department of Applied Physics, Applied Mathematics. This is the research group that I'm in. I do a lot of work as the lead software engineer for a research group, mostly for streaming data processing and data provenance, combined with advanced X-ray scattering experiments. I do a lot of work out at Brookhaven National Lab. This is like an X-ray machine, but $1 billion worth of X-ray machine. Very expensive X-ray machine. I also do work as part of a core developer of Conda and I'll talk about this a lot later. All right, so motivating catastrophes. For the record, these catastrophes have all happened to me. So I got all the kind of nitty-gritty details. So I broke my advisor's machine, and I've broken my own machine many a time. So I had some great software. Like, it was some cool stuff, and my advisor was like, that's perfect. Install it on my machine, I'm gonna run it for myself, I'm gonna like play with all the slider bars, all the parameters, let's go. All right, let's go. I go to install it. Doesn't work. They're missing some software. You know, Python says couldn't import blah blah blah. That's fine. Like, come on. We'll just install blah blah blah. Not a problem. But of course, that version of that library wasn't actually compatible with the software that they had on their machine, or maybe that software is missing other software. And you know, worst case scenario, your advisor has a grant due tomorrow, and you've now broken their text editor. So yeah, I was just playing with my imagination, and everything ended up burning down. This is not an advisable situation to get yourself into. All right, another example. One of my colleagues, or reviewer, or journal editor, or maybe one of my research frenemies, decides that they want to rerun my analysis from scratch. Great. I have code. Maybe it's in a script, or if I'm getting super fancy, I have an entire Jupyter notebook that does my analysis. Just send it to them. They run the analysis and get different results, which is kind of, you know, one of those bum, bum, bum moments. And I start sweating bullets because maybe my math was wrong or my coding was wrong. Did anyone see recently there was an article about water? Apparently, for years, two people were fighting back and forth about how water worked near its freezing point. And in this case, the much better known person actually had it wrong. Their code had errors in it. But they fought tooth and nail saying it was correct until finally they had to release the source code. And someone finally found the error. So this is fairly common occurrence because maybe they're using actually different dependencies than I am. You know, minor versions of some things can actually produce major errors, as I have found out the hard way many a time. Sorry. And then, of course, I've broken my own machine a whole bunch of times. So I found some cool new library. Not only does it tune my deep learning hyperparameters, it also makes espresso for me, which is kind of the perfect combination right there. I installed a new library, not a problem. But it needed a newer version of NumPy. So I went and changed the version of NumPy that I had. All right. But now none of the software that I wrote to, you know, like produce my thesis works. It just all broke. Again, I start sweating bullets because I'm trying to graduate in May, so this will not end well. And so different versions of dependencies potentially cause a whole bunch of conflicts when installing new software or even just kind of updating software. So all of these kind of motivating examples, I would call them catastrophes, but I'm kind of dramatic with that, can be addressed with packages and environments. So really the problem was that we actually, as humans, did way too much work in all of these examples. We really should have let something else do all the work for us. in software engineering, laziness is actually an incredibly important trait in software engineering. If you're not lazy, you're not doing it right. So I'm going to talk, as you can see at the very top here, from kind of three perspectives on kind of the packaging and environment and ecosystem problems. The first is the user's perspective. If you're some PI and you're not running code, but you want to use code, maybe, that's great. This perspective is for you. This is how to get code, how to install it, how to make certain it's all humming away. There's also a maintainer's perspective. So if you're writing code and you want to share it with the universe, how do you go about doing that in a way that it is reproducible and won't give you tons of headaches 6 months from now? And then finally, we're going to talk a little bit about kind of the engineer's perspective, which is really kind of my perspective in terms of how this all works from behind the curtain. What gears are moving when you make packages or download packages. And of course, I'm more than happy to, if anyone has packages they want to build, especially for Conforge, I'm happy to try to help out with that. I can run a demo of me uploading a package on the spot, and any questions and whatnot. I guess I'm planning on there's some hands-on tutorials for these two sections, and some breaks, because I think I have some water lying around here somewhere. So what are packages? Well, these are what packages are. So these are some of the first packages. These are canopic jars. They're used in the mummification process in ancient Egypt. These were used to store organs during the mummification process. These were typically entombed with the mummy and a whole bunch of very shiny and culturally important objects. Packages. Is that packages then? Packages now. Now packages look like these. They're used for shipping goods throughout the world. They don't usually contain organs anymore, though. I don't think I can order a new pancreas from Amazon yet. You're all giving me very blank look. Oh, you mean software pack? Okay. That explains many things. I'm not Egyptologist. So, okay, software packages. So software packages are a way to get, install, or upgrade software. Usually consist of two parts. They contain metadata about your software and either source code or compiled binaries that represent your software. They generally have external software for managing their installation. This thing is called Package Manager. This is actually the cool bit. Packages themselves are kind of boring. The package managers are super cool though. Kind of an annoying caveat here. In the Python world, Python overloads this term to mean a folder with a double underscore, also known as dunder, init.py in it, which we'll talk about more later, but you just need to be kind of cognizant that there's two modes. When Python says it's a package, it's a folder. When I'm talking about packages, it's your code plus some metadata about your code. Okay, so what is a package manager? I said it was super cool, so I guess I should describe it. So a package manager is a piece of software whose jobs are, one, to download your packages. Usually this means that it needs to know where those packages live. Generally they're on some web server somewhere associated with the URL. Usually most of the advanced package managers keep track of a database, and that database knows where all the things are and what they're called and what versions they have and a whole bunch of other nifty information that your package manager might want to know at any point in time. It knows how to install your packages. So once it grabs the packages from the net, it can go and properly put them on your computer in such a way that your computer knows how to find them and use them. And maybe install them if it needs to. If it needs to compile code, it'll compile code. If it needs to do some sort of dynamic linking, it'll do that too. And it knows how to update packages. And so you're able to tell your package manager, I would like new copies of everything, please. And it can go to the database and say, well, if there are new things, go download it and then install it. Note that these three things, although incredibly important and really nice, are not that spectacular. Frankly, you could do this with just like a wget or a curl. You could install the packages with just Python set up to py, and you could update the packages by saying, I don't care about elegance, just let me get everything installed again from scratch, please. The really cool part about package managers, though, is this bit. They keep your system self-consistent. The way that it does this is that if you have like 100 packages on your machine, how do you make sure that they're all compatible? Maybe they need different versions of different things. This is kind of like the wolf, sheep, cabbage problem, but with an entire food web. For those of you who haven't heard of the wolf, sheep, cabbage problem, the idea is that a wolf, sheep, and a cabbage are sitting on the bank of a river, and it is your job to take them across the river. However, if you leave the wolf with the sheep will eat the sheep, and if you leave the sheep with the cabbage will eat the cabbage. The cabbage will just sit there. And so the way to solve this is to conditionally transfer things back and forth depending on the exact state that you have right now. So these are 3 things, but I said you might have hundreds or maybe thousands of packages to worry about. Thankfully, we have math. Math is really good at these things. And this fits into a particular problem space in mathematics called a Boolean satisfiability problem. This is also called SAT. So usually you use something called a SAT solver to go and try to find some janky combination of all these packages such that they all don't blow up. And so the way we do that is that we express the web of dependencies as a graph. And usually this is a directed graph because one thing depends on some other thing, which depends on some other thing. Each node in the graph expresses what software it needs. This is also encoded in the edges. And then the SAT solver is going to try to check everyone's conditionals against each other and find some sort of very, very fine threading of a needle that gets your environment to work properly. Note that this needle, is not only small, but also hundreds of dimensions wide. So this is what the dependency graph for NumPy looks like. Each one of these red dots is an independent package that NumPy either needs to build or to run. By the way, how many people have used NumPy in the past? Just so I have like a... Okay, so most of you are kind of familiar with the scientific Python stack? Cool. By the way, NumPy is sitting over here. That dot is NumPy. I know that this could be a little bit difficult to read, but the main point is just that there are arrows and they point from here to here, and there's a giant web. Thankfully, we actually know how to solve these. The math is actually quite well behaved for these kind of problems. So package managers, do I have one? So most package managers are actually associated with the operating system. We're not going to focus on those, and I'll talk a little bit later why you probably don't want to use them for the most part. But if you're on Linux, pretty much every distribution of Linux has a package manager. On Ubuntu and Debian, you have hat. On Red Hat and Red Hat flavored things, Fedora and whatnot, you have Yum. If you're running Arch, kudos to you. It's Pacman. And if you're running Gen 2, it's Portage. Gen 2 is actually kind of the odd one out here. These are all binary package managers, and Gen 2 actually runs from source, so you have to recompile everything from scratch. Lots of CPU hours. So if you're on OS X, there's something called Homebrew, which is kind of, sort of, a package manager. It's not actually associated with the operating system. It's kind of this weird in-between thing where it operates with your operating system, but wasn't shipped with it and might not officially be supported. I don't really use Mac OS that much, so definitely let me know. On Windows, or if you have a smartphone, they're called app stores. And so we don't traditionally think of app stores as kind of traditional package managers for a couple of reasons, but they fit the bill. They know how to get your software, they know how to install it, they know how to upgrade it, and they know how to keep it self-consistent for the most part. So they definitely fit the bill. So if you don't have one, or if you don't want to use your operating system's package manager, that's totally fine. And actually, I would encourage this personally. The two main package managers I'm going to talk about today are pip and conda, which work on pretty much any operating system that you have, unless you have something super janky. We might not support some really weird flavors of Linux. But we support most things. And pip is shipped with Python. So if you have a copy of Python, 99% of the time, you have pip. That 1% of the time, by the way, is if you compiled your own Python from scratch, at which point you should take over the lecture for me because you really know a lot more than I do. Conda is provided by either the Miniconda or Anaconda distributions. There are links to those here if you'd like those. Personally, I prefer Miniconda. It's pretty much an aesthetic difference. Anaconda ships with a lot more things in it, some extra executables and whatnot. And Miniconda does. Miniconda is pretty much just a straight executable. It ships with the bare minimum packages it needs to run. But at the end of the day, once you start installing the scientific stack, Miniconda and Anaconda look pretty similar because they use the same package base. All right, so pip. By the way, pip stands for pip installs Python, which is a nice piece of recursion there. So this is Python's internal package manager. It's mostly a source distribution, and this is because Python's mostly an interpreted language, so you don't need to go through really heavy compilation steps. Although pip can install wheels, which are binary packages. So if you install NumPy via pip, that NumPy actually exists as a binary because NumPy exists in many parts. The Python API that you go talk to, and then a whole bunch of C, C++, and Fortran backends that actually run the numbers for you because those are much faster than Python for array computations. So they need to be shipped as compiled packages. Pip can do some cool stuff. It, of course, can install Python packages, so pip install 6 is a valid command. It can also install packages directly from Git. So if you say Python install git plus git, and then some sort of URL, usually GitHub, it will actually go and install Django Oscar from master branch on GitHub. And there's some other extra syntax you can add in if you want to go from tagged versions instead of master. But this is super cool. And then the coolest of them all is installing editable packages. This is very similar to Python setup.py develop, which is a really important tool while you're building code. What this does is that instead of taking the entirety of your source code and copying it to a Python-owned directory so that Python could go then find it, it has a pointer, it puts a pointer in the Python-owned directory and says, go look here for the source code. What that means is that you could go dynamically change the source code in some Git repository or some sort of version control, please, I'm begging. And all of your code would automatically be interpreted by Python and be usable. So this is great if you're tuning a library or you want to run some tests. One downside is that pip doesn't have a stat solver currently. Stat solvers, although well understood, are a fairly hefty chunk of mathematics and are usually written in low-level languages like C, C++, and whatnot. And although there have been some implementations of a stat solver in Python, pip hasn't started using them, and they've been fairly adamant about not having C extensions inside of pip for fairly decent reasons. It would be really weird if your dedicated Python package manager also needed a whole bunch of compiled C code. However, on the user side, this produces some headaches. Because it doesn't have a stat solver, it could do some weird things to your environment when you say to update code or install new code. Because it doesn't do as good of a job checking that versions are compatible with each other. So, kind of buyer beware. Yeah?
What do you mean by wheels?
Okay, sure. So wheels are a dedicated format. I think they're actually tar format, but they're a tar format where when you go to make a package, there's a specific command for pip where you can, or step.py, where you can go make a package and compile it. So you make the binary code, and the wheel is the way that you kind of tie that all up with string, and hand it to the Python packaging authority. So this is kind of their format for how to ship around binary code. Does that answer your question? Okay. So Conda is kind of the other Python packaging system. So not blessed by the Python packaging authority. However, it's a binary package manager, meaning most of the hard bits, like the compilation we were just talking about, where you need to compile the source code, are done ahead of time. Now this is kind of trivial for Python, but not trivial when you're shipping things like Fortran, which is really rough. Importantly, and I should have mentioned this with the pip as well, Conda doesn't touch your system packages, and it does not require privileges to run. This is a wholly user-spaced operation, so you could, on a machine that you don't own or don't have privileged access to, copy the mini-conda executable, have it install, and it will just produce some folders in your home directory, which you then can put packages into. So this is like super common on shared machines where it's under some sort of system administration. Pip works similarly, with one caveat. Usually your operating system has a copy of Python in it. And if you don't have any other Python installed, when you say Python in your terminal, it goes and pokes your system installed Python. When you say pip, it pokes that self-same Python. This means that you could pip install things into your operating system's Python, which is a really bad idea. Like, your operating system has a really great package manager usually, if you have a package manager with your operating system, and it's really good about making certain that your operating system doesn't break. And if you start installing things into it that your system package manager isn't aware of, weird things could happen. However, if you have other Python installs, pip will work just fine. The real gotcha is the second you start having to say sudo when you're installing packages not for your operating system, you probably should step back and think about exactly what you're doing and whether or not you're doing it in the kind of sanest way. Importantly, Conda installs more than just Python. So obviously it can install nice chunks of the scientific stack like NumPy. This is what it was originally built for, was servicing the scientific Python stack because so much of it is compiled. But you can now also install other languages like OCaml or R or Lua or even MikTeX, which is a Windows LaTeX compiler. You can also install ulibc and Clang and Fortran and pretty much, if there's a language that we don't have yet, it's most likely because no one's asked for it. So here's kind of somewhat hacky decision tree. What package manager should you end up using? So you're just going to use the software. You're not going to build code on top of it. You're not going to poke it really hard. Using your app, Yum, Homebrew, App Store, it's totally fine. I wouldn't want to try to Conda install Microsoft Word or Chrome for that matter. You're just going to use that software. I don't even know if Microsoft Word has an API that you could go poke. And these are totally fine. Your operating system will do a really nice job of making certain that these work. By the way, these are also good for things that really touch the low level of your hardware. So like Steam, which installs packages that happen to have lots of GPU support because they're video games, I would put kind of in this category. If you're just going to use them, you're not going to poke them. If you're going to build on these things, which means that you're going to install and uninstall, you're going to not want to depend on your operating system for the C compiler that you want to use maybe. Because if you're running Red Hat, your C compiler might be ancient beyond reason. Your Python certainly is. I think Red Hat's still on Python 2.7. They haven't actually shipped an official Python 3 yet. You're definitely going to want to use either one of this language-specific package managers, so pip for Python, npm for JavaScript, Maven for Java, or if you want to use more than one language, and probably most of you will since you're all working in the scientific stack, you're going to probably want Conda. So as I said before, the system package managers are really designed to work with your operating system. When you actually go and install things, you probably need privileges. On Linux, this means you need a sudo. On Windows, this probably means a pop-up shows up with that little weird shield thing that you need to click to say that you're an administrator. You probably want to use a user space package manager so that it doesn't interfere with the operating system. Similarly, yeah, the second you say sudo pip install or sudo conda install, rethink that, please. Because this is what happens when you don't. This is a comment from XKCD noting how difficult it is to keep track of Python environments and where Python points to. The most kind of an interesting bit here is this thing called Python path. Python path is a list of paths on your computer. And Python, when it goes to try to import a library, it goes through this list in order and says, can I find it here? Nope. Can I find it here? Nope. Can I find it here? Nope. If it goes through that entire list and can't find it, it'll yell and say, import error, I couldn't find it. However, lots and lots of things poke this thing, potentially. The alt text for this was discussing about sealing this environment, this potentially radioactive environment, under a mountain and leaving pictorial evidence as to never using sudo with pip. So we're going to try to avoid this. And the way that we're going to avoid this is with virtual environments. So virtual environments are a way to prevent software from bleeding into one another for projects. And this allows you to do some really cool things, like have completely different dependencies on your system. For instance, with the Conda environment management, you can actually have multiple versions of Python on your operating system at once and running side by side. They can't talk to each other, but you could run legacy things in Python 2.7 and run brand new things in Python 3.7, no problem. They also provide a lot of safety. So if one environment goes belly up, you just get rid of it. Again, because I use Conda a lot. The Conda environments are just folders on your computer somewhere, usually under some directory under home. You literally can just go delete folder, and that environment is gone. One of my experiences with this, I think I uninstalled Matplotlib in my environment and installed it from source because I wanted to play around with some new features and give some feedback. And then I was done with that. Maybe it didn't work or something. So I uninstalled my locally installed one and tried to install it again from Conda. And apparently it had delinked all of my C libraries from Python, which meant like nothing worked. NumPy, SciPy, nothing. The worst errors that you ever saw, like unintelligible things. Okay, that's not fair. They weren't site faults, but they were still pretty unintelligible. You just declare Conda bankruptcy, delete the environment, make a new one. Note that this would be really, really hard to do with your system package manager. You pretty much just have to rip your entire operating system out because your system package manager is so integral to its operation that, and you only have one environment. Your environment is your computer. You can also ask the environment for the current contents with version numbers and potential URLs as to where you got that code from. This is super important for reproducibility. This actually addresses catastrophe number 2. If I had sent to my reviewers the environment that I ran the Jupyter Notebook in, they'd have a much higher probability of actually being able to run my code successfully and getting the same results. Alright, so there are a bunch of environment managers for Python. So the one that is kind of the very standard one is virtual env. So you can create virtual envs by just saying virtual env. Env has lost all meaning to me now. There's pipenv. This one's also fairly popular. The one that I use is Conda. So Conda actually combines both a package manager and an environment manager. So you can say conda create -n, so this is the name of your environment, and then we'll install Python 3 into it. Once you've created an environment, you can either say source activate env or conda activate env. I think conda's been moving more and more to this kind of thing, but I still use source activate because don't fix one, ain't broke. you can then install software kind of into that environment the normal way. What happens is that the environment manager preempts your path in such a way to point to the correct copy of Python. So when you say pip install, you're no longer using your system pip, you're using actually the pip that is associated with your environment. Same thing with conda install. So to upgrade software is usually fairly straightforward. So conda update numpy tries to see if there's a new version of numpy and install it if possible. Sometimes it will fail. Sometimes it will fail with a not solvable error. And this meant that a newer version of numpy conflicts with some existing software and that they couldn't update the existing software to also be compatible with the new numpy. So it'll just fail. And at that point, you need to make some decisions about, do I really need that software, or maybe I need to make a new environment. Pip does the same, kind of has the same deal. Pip install dash upgrade. You could also just say pip install numpy, and I'll just try to get you the newest version. So this is kind of the hands-on section. All right, how many people have a copy of conda? Okay, so we can mostly skip this part. Although you should totally test that it works. You know, conda dash. Oh, sorry, I missed a dash. Dash help or dash 8. So we can go create a new environment. I'm going to. Has everyone got the instructions? I'm going to flip over and do it myself. So, no. Conda, yay. You can kind of see that I did run through these demos last night to make sure that they're. Can everyone see that? So when you run this, it is. Oh, it's going to fail. Anyone want to take a stab as to why this totally failed on my computer? No. I don't have an internet connection because I've never been in this building before. So I should probably connect to the internet at some point because it has to go to the internet for the database.
Go to MSK, yes.
Okay.
MSK.
Is it going to ask me to do something via a web browser?
Yeah, it should pop up and it should, yeah, and you
Cool.
click.
Okay, that's fine.
And you accept it.
By the way, that's why it's complaining about HTTP. And while that's happening, I will flip back to there. So that. Come on. Hey. Yeah, no, I'm connected. It's lovely. Always have a backup plan. Sorry. It's funny, of all of the, things that I ran through in my head last night about all the things that could go wrong, this was actually not one of them.
Is it not popping up?
It isn't, but that's okay. I have a phone. I can just use my phone's internet. Okay, where were we? Try that one again. Yay! So this is the solving part. I have been told by a reliable source that this will be faster in newer releases of conda. It's a little bit slow right now because it's actually got a ton of things to work out. I can't move from the podium. Note that we specified Python 3.6 here. You can do that also with pip, where you can say something, something, something equals something. You can also add greater thans or less thans or greater equals or less equals. Great. So now it says, I need to install all of these packages in order to get this to go. Note that one of the things that's in there is pip. So pip installing into a conda environment, not impossible, but doable. So it's now going to go download them. Notice it also got wheel. Again, Python loves overloading things. This wheel here is the library that makes wheel files. Okay, and you can see here that it says source activate pack demo. So I'm going to go do that. Oh, right, sorry. Don't look at that error. I have this alias. Come back here. No, not that one. That. Sorry about that. I'm running an incredibly awesome, but sometimes janky terminal called Conch, also pronounced Zanj. So there are some things that play with Conda. Anyway, so you can see here that in the left-hand corner here it says pack demo, and that's telling me that I've activated my environment. I'm now running from this environment. Virtual env and different shells might be a little bit different, but they usually show something to show that you're in an environment.
Mine suggested I use conda activate. Is there a difference? Why yours is source and mine is conda?
I'm not exactly certain. So I might have an older version of conda for one. Conda has been moving towards conda activate. I think they both still work, but if it says use conda activate, you should follow their instructions because they're most likely correct. I think the next thing. But did everyone get to kind of this point? Okay. Did anyone have any problems getting to this point? What were the problems?
It's just telling me that conda doesn't exist.
Ah, okay. Do you have conda installed?
Yes.
You might need to go. Do you have you're on Windows?
Yes.
Okay. Is there like an executable for conda? Like there's a shell or something? Usually, like I know that Anaconda ships its own dedicated shell. Because Windows does its own thing. Did anyone else have issues getting an environment going? This is the hands-on section, so I'm happy to troubleshoot and whatnot. I am rooted to the spot, so you'll have to call out what the problems are. But okay, did you find the shell?
Yes.
Okay. I can put the instructions back on.
I have the slides.
Oh, okay. Well, I also want to put those out for my own benefit because I need to know what happened next. All right, so we're going to install NumPy 1.14. So conda install NumPy. Now, note that I'm putting this -c conda forge at the end. So conda has an idea called channels. And so the idea behind channels is that many people might want to make conda packages. And that's totally great. And maybe that you have some special needs for your particular copy of NumPy. For instance, you're running on a supercomputer and you specifically compiled it for the PowerPC chipset that you're running on. Or maybe you want to run this on a cell phone and you compiled it for the ARM chipset that runs in most cell phones these days. That's totally fine. And the way that we handle that is that you can upload those to channels. So CondaForge has a dedicated channel. Each person could have a dedicated channel they're free to make and whatnot. But by specifying -c, we explicitly say that we would like to get NumPy from CondaForge, please. And we'll go through another round of solving. This is going to be a much bigger install because Python's kind of smallish, but NumPy, SciPy, and whatnot, less so. Okay, so we're going to install some stuff, including an OpenBlob. I was talking about OpenBlob later. Yeah.
Sorry, just because sorry, it's a silly question, but should I be using Anaconda prompt moving forward?
Yeah, please.
Instead of the bash terminal or Windows command?
Yes, please. Yeah, no, thank you. I should have mentioned that. Yeah, there might be ways to get them all to play nicely with each other. I just don't know them. And so I don't know. I don't want to give out advice that I can't actually follow up on. Okay, so we can install NumPy. Note here, this is actually where this folder lives on disk. So we could go there and poke it. So, okay, so it's going to go, make sure we get all the code. Right, executing. Great. But NumPy 1.14 might be a little bit old for us. So maybe it would be better to go with a newer NumPy. So we can go do that as well. So we can get, say, conda update. So note that we haven't put a version constraint on NumPy here. It's just going to get the latest NumPy, whatever we can get, we're going to get. And in this particular environment, that's going to be actually pretty straightforward because we have very little things installed. We don't have a scikit-learn or a scipy or a matplotlib that we need to worry about. So now it's going to update us from NumPy 1.14.6 to 1.15.4. That's totally fine. Okay, and kind of the last bit of this is now that we've gone and made an environment, we've installed some things, we've changed some things, we'd really like to know where we are. So conda list is a good way to do that. So if you say conda list. So this lists all of the packages that are currently in this environment. You could plumb this down to a file somewhere. You can ask for it in JSON format if you wanted to read this into a piece of code. You could ask for this extremely explicitly. And here, they just give us the URLs. That one. So if you really need to get really nitty-gritty, reproducible environments, conda list is a great way to inspect what you currently have installed. Note that it will also list pip packages if you have them installed. Not this way, but if you say conda list, it will also include pip packages. So let me open up a new terminal and source activate into one of my production environments. Conda list. And you can see here that there are some pip packages here. Note that these are actually source installed. They're not actually installed from pip, but conda only has like two modes, conda and pip, so they're called pip. Sorry?
Is it the same conda list?
Yeah. So if you had pip installed things, you could go and say that. So let me actually try that. So if we say pip install streams, I'm going to be using streams a lot because I know the pure Python and I wrote some chunks of it. Oh man. So you can see that pip's downloading a whole bunch of dependencies. Oops. One of which might have been pandas, which is probably a bad idea. You probably wanted to get pandas from conda. But that's okay. We will destroy this environment when we are done with it, and then our mistakes will be erased. Conda. And you can see that there are some things installed from pip now, including 6, tools, and tornado. And so, does that answer your question? Those are listed as pip. So Python setup at Py, develop, or Python setup at Py install are listed as pips. And you can kind of tell that these were installed from source because their version numbers are a little bit wonky. Oops, yeah.
So when you install from pip in a conda environment, is there still some stat somewhere that goes on about keeping everything consistent, or it's just like you could destroy this environment?
Yeah, it doesn't have a stat solver, so it doesn't
Like the environment, but the conda doesn't interfere with that when you're in that environment.
Currently, conda doesn't get in the way of pip. There is some discussion, I think, going forward about what the future of conda and pip are, and part of that discussion was, should conda get in the way of pip? And when you say pip install something, if conda can find you a conda version that it can run a sat solver on, it will just like subtly, or maybe not so subtly, hand you that one instead and say, well, we thought you would prefer this. I don't know where that conversation got to. I guess we had that discussion at AnacondaCon, which was June, May, somewhere in that of this year. But I don't know if we've all solidified the solution yet. Again, at the end of this talk, I'm going to show you all how to package things onto CondaForge. So you may not have to use pip that often, depending on how you actually run your workflow. So that's the whole gig. Speaking of gigs, let's see. So this is my mini Conda install. So you can see it's got a whole bunch of stuff in it. But let's go inside End. So these are the list of all the environments that I currently have, which is probably a few too many, but they're really cheap to make. When we go into pack download, this is what that looks like. And this is 278 megabytes. So, sorry, I just ran a quick command to get me all the sizes. Yeah.
So, let's say we're doing something a little bit larger than this.
Sure.
And we need to put
Yep.
Is that going to duplicate the existing packages on the system, or is it just going to point links to dependency so that it can lower the total load of the environment?
I think currently they duplicate them, mostly because it would be very difficult for Conda to make certain that if it had shared, for instance, Python versions amongst environments, whether or not it could update them. Like, environments are fundamentally designed to be hermetically sealed. And they won't compromise, and they'll work really hard to not compromise that. And so I think there are worries about whether or not you could break those environments by updating a different environment. Pip might be different. I'm not exactly certain how virtual env handles that. So yeah, this does take up some space on your hard drive. I think currently all my environments are like 7 gigabytes, but just as an example, we could change over to dpdev, which is my data processing dev system. Okay, actually that's a lot better than we thought. 4 gigabytes. Okay. And you can see here that this is Python 3.5, which is a little bit scandalous because I really should be on Python 3.6 at this point. This is where a lot of the things are taken up. So if we move into that directory, you will see why. This is actually where all of those things got put. These are all of the packages and whatever shared object libraries, our C code produced. This is all the nitty gritty. Usually one doesn't look at these things, but they're there if you want. Note that these things, these egg-link things, these are for software that is Python certified developed. So these are our links that we were talking about earlier, where it just points to my source code on disk locally. I don't actually know what's inside of those. We could find out. Sorry for all the Emacs people. Yeah, okay. That's kind of what I expected it to look like. So this is where it lives on. This is where this particular project lives on disk, and it's just a pointer. It says, "Go look there."
Where is this environment directory supposed to be? Is this something you set up? I want my environment to be saved in a file. Set up by Conda.
So this is set up by Conda. So MC is where I install my mini Conda version, and then Conda goes and provisions all the folders it needs. Back to your question just briefly, Conda will yell at you if there's no longer enough space on disk to install packages on, which I totally ran into last night. And then I deleted a whole bunch of environments that I decided I really didn't need at the end of the day. So, yeah. Okay. Yeah. Oh, sorry.
Can there be times, I mean, I think I've seen this happen in the past, where you're in a certain environment and you import a library and it ends up importing a library that's not in that environment? Or is that impossible? Or when would something like that happen?
Ideally, it shouldn't be possible. So, I don't know if this is exactly what you're asking, but I have run into this before. And the place where it usually happens is in IPython.
Yes.
Okay,
Yes.
so this is what happens when you don't have an IPython installed in this environment. So what happens is that when you say on the terminal, IPython, ooh, I can actually do it right here, I think.
That's so neat. Oh.
Ah, okay, so this one's actually really smart.
Is that because you're on couch?
Yeah, probably. No, don't do this, please. That is a bad idea. So let's see if I can do this in a different terminal. No. Okay. So this is actually because I don't have an IPython installed in my
You don't have anything.
But if you did, and you didn't have an IPython installed in this directory, or this environment, which you probably don't because we didn't install it, what will happen is that it will fall back onto the system IPython because it's in your path somewhere. It's in user bin or something. And so that's a totally valid path for your computer to find it on. At that point, you're now running on whatever Python version that IPython was running on top of. Which means that 90% of the things that you install might not be there because that's your system Python. You hopefully didn't install NumPy into it. Is that kind of...
Yeah.
Jupyter Notebooks also do this if
Right,
you don't have Jupyter installed.
But the environment does not protect against that. Like if you call IPython, it doesn't give you an error because you're in that environment and you don't have IPython installed.
Right, unless, like me, you literally don't have IPython installed.
Now, why don't content environments protect against that? If it's supposed to be hermetically sealed and only see things that are inside the environment.
Because the system takes precedence over conda. So the issue there is it's not a conda problem so much as when you run an executable, your operating system has a list of things that it goes through. And although I love conch. This would have come out as some giant string blob in regular shell. Instead, it comes out as a nice Python list. So you can see here, actually, this is what the virtual environment did. Just for the sake of argument, let me do it here. This is a brand new conch shell. So you can see here that this is the order in which Linux will go and look for executables. It'll first go to home/minikconda/bin. This is the miniconda top level binary. That's because I specifically asked for that in my RC. Then it'll go to user local sbin, and then bin, and then user bin, sbin, and then user bin, and then sbin, and then bin, and however, in here you can see that miniconda bin has been replaced with packdemo bin. However, if you don't have an IPython here, it's going to go look in these. And if you have an IPython in one of these, it's going to find it. So there's no great way for Conda to fix that problem without hacking your operating system to not look for things that it should own but doesn't. I don't even know how it would know whether or not it should own something.
So once you're in that IPython, it will only see the libraries that are in your base.
Yeah.
Okay.
So for instance, I can get a similar effect here. So cool hint given here. Did you read one of the following? Python points to my packdemo Python. Python 3 also points to my packdemo Python. The command Python 2 doesn't though. That points to user bin Python 2. We totally installed NumPy into this environment. Ooh, and we have one here too. Can I ask for tender version? So this is actually a really, really nasty bug. Like you would have ended up in this Python thing, and okay, the Python 2.7 was a dead giveaway because no one's using Python 2.7, right? Like everyone knows that in like a very short amount of time that thing's gonna die real hard. Like all the scientific stack is gonna stop supporting it in 2019, I think, or maybe it's 2020, but real soon we're gonna stop. But if that wasn't a dead giveaway for you, and this wasn't a dead giveaway, once you imported NumPy, this looks reasonable. Like you successfully imported NumPy. It should have blown up. But if you go and ask for the NumPy version, it's ancient beyond all reason. Yeah, you should be careful about this. And kind of one way to do this, I think at least on Linux and potentially OS X, is which. So which is a command for Unix operating systems, and maybe Windows has something similar that I don't know. Maybe it's dir. It'll hand you back the path to whatever command, assuming it exists. Now, Conch complains particularly nicely, but your shell would also kind of complain and say, I don't know what that thing is, it doesn't exist in the path, it's not bothering me. So this is a good way to double check that you're pointing at the thing that you should be pointing at. Yeah?
I think it's not, but just want to check. Is the path applies to all the environments, and we don't have environment-specific different paths.
Right, so
Avoid this, and can I remove this from the path?
So the path is something that your operating system creates at the time. The virtual environments go and modify the path so that they place themselves first, so they get resolved first. You can, although I would not advise it, access your path in Python. Python? Nope, you don't have Python. So, conch also is valid Python, so I can do things like import this. You could do this in a Python or IPython terminal, though. And you could say system-path. And that will report the complete and utter path that you currently have. This is your Python path, for the record, though. Note, however, you could go modify this. It is ill-advisable to do so, because this is how Python finds all its packages, but you could totally do it. You can also do that to your path, like your operating system level path. You can go add things to it, pop things from it.
It will affect all the environments.
Right. Although this one is specific, I believe, to this environment, because I have it. No, it's not. Okay, that's not specific to this environment. No. So how? Yeah.
Sorry.
Oh, okay. Yeah.
If someone, let's say we're sending our software code to a friend who wants to run it, would you send them the print out of that conda list, or would you send that environment directory to them?
So sending environments directly is actually a non-trivial thing. There are some tools to do it, but some of the tools are getting deprecated, and some of the tools are being written. So there's not currently one great thing in the middle there. What I would do, if you want to be really nice to this person, is to you can do stuff like conda list my conda list. So I just piped this into a text file. Or you could pipe this using you could use the -JSON, and then that would be JSON. Conda actually has a way to look at these kind of files and probably parse out the things. So you could say Conda create m-file and hand it a file, and it will properly reproduce that environment to the best of its ability. There are some things that it won't be able to reproduce, for instance. So there are some Windows-specific packages, like mysys2, that aren't needed on Linux. And so it would be like, well, I can't find mysys2 if you're trying to go from Linux to Windows. Or sorry, from Windows to Linux. But yeah, I think this is a good start. Personally, I much prefer text files to screenshots. These are parsable. Yeah.
At the beginning, when you create the environment, you upgraded a bunch of packages because it's required, I think, at the beginning. Do I have to upgrade it? Or, I mean, because I'm worrying, at that time, it's in your, it's not in virtual environment, it's like the main system. I'm worried if I upload it in Conda, then I cannot reproduce the previous data generated with the old packages.
So when you go and say conda create -n, that runs in a new environment. And we didn't actually update, we actually newly installed. So we download brand new packages for this environment. But if you're worried about that, and kind of, this is a good kind of thing to do in general, is you should keep conda lists of all of your production quality environments. That way, it's kind of like backing up your computer, but cheaper because it's only like, 100 lines of text file. Rather than an entire overnight terabyte backup. This will also be really helpful if you install something and it destroys your environment. Because then you can just say, well, I know exactly what environment I wanted before it got destroyed. Because I have this conda list thing. You probably could set it up as a really cool cron job to run every night or something.
But once you get the conda list, the basic system list, where the directories, do I have to go to them, get them one by one, or is there an easy way to install something from conda list?
Give me 1 second. I'm going to actually pull up the docs for this, because the docs are going to say it much better than I ever could. Okay. Building identical content. So this is their work. Can I read that? This is the content.io documentation. The documentation is really nice. They've got lots and lots of stuff there. It's all nice and searchable. So they say to run content list explicit. So we ran that. And then you can say send it to a text file, which we kind of sort of almost did. And then finally, let me know if I'm going too fast. Here you go. Conda create name -- file, and that will reread the file and reproduce as best as possible. Note the caveat here that if you're on a different operating system, they might not work exactly the same. So you should be a little bit careful about that. But because it's an actual text file, Conda will probably produce an error saying, I couldn't find package XYZ on Windows. And then you might just remove that package and see if it, kind of just iteratively keep removing packages until it installs. Because if it just says like numpy, scipy, that's fine. Like there are those for Windows. I can guarantee that. Yes, even on 32-bit.
Do you think this will try to conserve the conda channels?
So actually, those are supplied. So if we say conda list -- explicit, cool. You'll see here in this that it's got conda in it. So this is an actual URL to an actual tarball that lives somewhere on the internet. I could actually try to go to this URL. This might actually. No, don't copy. Let's use this as a valid URL. I don't want to download it though. So, will you give me access? Pretty please. Hey! That looks like something. So this is a listing of all of CondaForge's no-harsh packages. Every single one. And then you just address a specific tarball. Like I said, you could actually do this with wget. And I think actually Conda might have a curl dependency internally to do all the going and getting and downloading stuff. The important bit is the self-consistency. Other questions? How's everyone doing? We can take it. We're at the point for I'll do this recap, and then we can take a break if everyone wants a break, or I can keep going. So as a recap, so a package manager is a piece of software that keeps track of other software, pretty much, on our behalf, so that we don't have to think about any of these nasty problems. You most likely have a package manager, especially since this seems to be a very content-heavy crowd. Congrats, you have a package manager. And some package managers are for building software on, others are really just for installing software that you're going to use. You probably don't want to go get your Wi-Fi router or your Wi-Fi driver from Conda. We don't have that many Wi-Fi cards to build against. We also fixed a couple of our motivating catastrophes. So we can send our fellow scientists environments by printing out what's in them with our code / notebooks, and that'll make certain that the results are reproducible. By the way, one could consider, it might be a little bit hefty, but you could do it, just making one environment per paper, where you wrote the paper, you generated all the figures, and you never touched that environment again, never update anything ever. That's fine. Or maybe every time you make a paper, you keep track of this Conda listing so that on demand you could recreate that environment to go make the figures again. Environments allow us to make certain that our system is not only just self-consistent, but it's also self-consistent across different projects, so that we don't run into any nasty conflicts where APIs have moved unexpectedly. And then package managers themselves will do their absolute best to make certain that your computer is left in a state after an install, making certain that things are compatible to the best of our ability. We are limited by the amount of metadata that is provided to us. Speaking of which, our next section is going to be all about that metadata, specifically the maintainer's perspective on packaging. 5 minutes, 10 minutes?
Let's do a 5 or 10 minute break.
I go last.
So, Act 2. So then I'm going to switch gears a little bit from the user's perspective. Sorry, I stole your chair and then I couldn't sit on it. So the maintainer's perspective. So this is really, you've written some code, usually in the form of a library. So usually we don't package just scripts together that much, because they're not usually that reusable outside of the context that they're written in. But you're in a library, you're going to do some cool sequencing or something. How to make a package is what this section is about. Sorry. All right. So hopefully I've convinced you that packages and package managers are pretty awesome, that we should totally use them, and they're great. And usually they just work. But what if we want to share our code? Or how do we make packages? So the broad strokes of getting ready to make a package. 1, you should absolutely test your code. Please test your code. So you should write some tests. You should document your code. You make certain that your code is installable. So in Python, this usually means having a setup.py. You should release a tagged version. So if you're using Git to track your code, you should totally use a version control system to track your code. You can make tags that denote that this code is ready, it's self-contained, it's ready to go. And then finally, upload the code or update a recipe or add the recipe, and your package will be released for the world to consume. Testing code and documenting code, although super important, it's kind of out of scope for this talk, because I'm sure that I could give, this talk would then have been 9 hours long. So how many people have written libraries? Okay, 1, 2. Okay, so a couple people have written libraries. I totally encourage you to write libraries. They're really great. They're a great way to. Yeah.
I don't know what's a library.
Okay, so that's a good question.
It's same thing as a package.
So packages and libraries are usually synonymous, but I guess my main point is
as opposed to just a couple scripts. So scripts are great as well, but libraries usually consist of functions and objects and variables that you'll want to access more than once. So like NumPy is a library. It actually doesn't have any scripts associated with it. But you can have scripts associated with libraries. So for instance, Dask is another library, but it actually has some command line scripts. Okay, so a couple people have written libraries before. What languages did you use? Python? R? Okay. Okay. I was wondering if I was going to get any stats from here. Cool. And thank you for not saying C and C++. If C and C++ are what you need to do, they're what you need to do. They're much harder to package now. All right. So this is kind of like my giant red disclaimer slide. So I'm going to talk about this in the context of Python. So far, I've been fairly generic. Conda works on everybody. But I'm going to talk about some specific things. Obviously, an R package doesn't have a setup.py. But it's totally fine. You can package other languages. That's not a problem. Just some of the nitty-gritty details are going to be a little bit different. Okay, so what is packaging, actually? So we said before that it contains two parts, data and metadata. By the way, this is something you can just pretty much say about anything. Everything's got some data and metadata about it. The data usually contains your code or a binary representation of your code, compiled down for whatever architecture and chipset you're running on. The metadata, though, is actually kind of more interesting. It has to contain at least two things, a name and a version number. You could technically get away with only those two things. It'll make life really difficult, but you can do it. It also contains a list of requirements, usually. So these are other libraries that you depend on. So for instance, if you wrote a Python library, at the very least, you're going to depend on Python. You're probably going to depend on things like NumPy, SciPy, and whatnot. Usually it also contains a description, so something telling you what the package is doing, what it's all about, and potentially a lot more data. Maybe you want to declare yourself as a maintainer of that package, or have a URL to the documentation. You definitely want to include a license for your package, which I will talk about later, I promise. Okay. When is code really ready to be packaged? Putting some variables down in a text file doesn't necessarily mean that it's ready to be packaged. Have you tested your code? At least a little. Packages are your way of sending around what you're doing and your thought process to the world. You probably would like to test that thought process before you fling open your doors and let anyone use it. You definitely want to document it as well. These don't have to be extensive, by the way, but they need to be there to some extent. If you're going to fling open your doors, some directions might be nice too. So this is Python specific, doesn't have a setup.py. Setup.py is kind of the standard way that Python and pip install Python packages. And finally, is it released or am I going to release it? Have you reached a pausing point in your development process where your test passed, there's documentation on all your things, and this could be handed to someone and would do something of value for them? All right, so this was taken from a talk given at SciPy this year called The Sheer Joy of Packaging. Really good talk, by the way, done by some of my colleagues at CondaForge and some other really great packagers who have actually a lot more experience than I do. And it's on YouTube. You should try to watch it. It's about 4 hours in total, broken up into a couple sections. So this is a traditional layout for a Python package. So we have bin. You could also call this scripts. So this is usually where you put your top level scripts. So if you have a command line tool, that's where that goes. Usually you keep track of a changes file. It doesn't have to be a text file. It could be markdown, restructured text, whatever you prefer. And it's nice to log the changes with each release. And this is a good way of telling your users what you did and between versions, so they know whether or not they want to upgrade or whether or not what they're going to get out of an upgrade. Docs. This is where the documentation lives. A license. So this is super important. If you find source code that does not have a license, don't touch it. When you write something, and writing software is considered writing something, it falls instantaneously under copyright. And that copyright is given to you automatically. You own that copyright until you decide to modify it or sign it away or anything. So without a license, this source code is not copyable because you don't have the right to copyright. You literally are missing the copyright. What these licenses do is say that I will allow you to copy my source code under certain conditions. Or maybe I'm going to say, I'm not going to let you copy my source code and be really explicit about it. There are a whole bunch of flavors of licenses, all the way from proprietary, which is literally, don't copy my source code, I'm going to ask you for money, to permissive, which is, yeah, fine, copy it, not a problem. Usually permissive licenses ask you to cite this source code and the copyright holder. And there's a thing called copyleft. And copyleft, I will come back to. So proprietary is pretty straightforward. You can't use the code, don't touch it, pay me money. Permissive usually has two major camps here, or maybe three. I think Apache also fits in this. So the two most common academically are MIT and BSD. And Apache also fits into this license system. Let's see. Open source initiative. Sorry, let me just pull this up. So there's something called the Open Source Initiative. I would like to. Yes. And they, thankfully, have a complete listing of all of their certified licenses. So these are the popular ones. So Apache, there are two BSDs. The way that the BSD license usually works is that if any piece of code is copied out of your code, it needs to be attributed to you. Full stop, no questions asked. All right. So then there's the GPL, GNU General Public License, and the lesser GPL, or LGPL. These are considered copyleft. And the way that these work is that if your code is copies any code under a GPL license, two things happen. One, your code has to go open source. Because for the second reason, that your code is now also under the GPL. It's what's considered a viral license, such that anything that copies out of that license is also under that license, which means that all of it goes open source. I don't know if anyone remembers Steve Ballmer comparing Linux to a cancer. This is why. The Linux operating system is under the GPL license. And so you can't actually reuse it in, for instance, Microsoft Windows. Or better yet, in Tesla self-driving cars. So this was a recent court case. Tesla copied huge chunks of a Linux distribution called BusyBox. It's really nice because it's super duper tiny. Like it literally just ships like the Linux kernel and maybe a few other things. No GUIs, no nothing. And they copied it verbatim. And then the courts came in and said that no, you couldn't do that. You now need to open source your modifications to that code that you made to run your cars on. It was a bit of a brouhaha. There are some other instances of this. It's good practice to keep up to date with these and make certain that you're doing them properly. MIT is also a permissive license. So this is like BSD, but there's a little bit higher bar needed for citation. So you can actually get away with copying a handful of things without citing the MIT code. There is a complete list of tons and tons and tons of open source licenses. Like everyone under the sun has open source licenses. Some of them are really interesting. Like the AGPL code license is incredibly aggressive GPL code. You can't even transmit it over a network without that code going open source. This, by the way, is what the Mongo database is licensed under, or was licensed under, until very recently was under the AGPL. And that's because their argument is like, either your code goes open source or you pay us money, kind of thing. So, okay, so that's the spiel about licenses. The OSI usually has a lot of information there. They have not only the text license, but sometimes they'll give you like a distilled version where it'll just tell you what you have to do. Note that these are software licenses. Text licenses, like for this presentation, which is under the Creative Commons 2, 1, and maybe 0 licenses for different chunks of it, are a little bit different. Most interesting of which is Creative Commons 0, which is literally no rights reserved, do whatever you want with it, run away with it. It creates public domain in countries that don't actually have public domain. So that's licenses. So you're going to have manifest.in, and this is a description of non-code files to include. So for instance, if you have some lookup tables in your library that you need to use, we have this a lot in X-ray land because we have tables describing how atoms interact with X-rays. Those might be included in your manifest.in so that Python knows to grab them as part of the packaging process. A README is usually really helpful. This is kind of the first stop on the way to your documentation, and tells me where the documentation lives and why you wrote this thing. A set.py, we're going to talk about next slide. This is kind of a script-ish for building and installing package. This is specific to Python. So here's where you see package name twice. So this is your package name. This is what Python's going to call your thing. So note that it's usually lowercase with underscores. This is because Python modules are usually lowercase with underscores according to the Python Enhancement Proposal 8, also known as PEP 8. Note that we have a dunder init.py. So that specifies that this folder contains Python modules, namely those two, and they should be made importable when we package them. Finally, there are two kind of modalities of thought on testing. You can either include the tests in your package, like this. Note that there's a test folder and it's got an init.py. The main benefit of this is that when you ship your code to the users, they can actually test whether or not your code works locally on their machine, and that's kind of great, because who knows, maybe they had a packaging issue. However, sometimes these tests get really huge, so some people like to leave the tests outside of the Python package. It's kind of, it's choice. Make it, yeah.
So, as people working in academic research,
so our in-house writer is the BSD3 clause, which I think technically says that the copyright is from the Board of Trustees of Columbia University in the city of New York. But usually your lab can establish a standard. BSD is fine, MIT is fine. GPL is usually enforced on you rather than chosen, but you're welcome to choose the GPL if you want. Do be aware that companies are really afraid of the GPL though. So if you ever want to kind of potentially give a company your code and it's GPL, they'll get really worried. A lot, usually. Yeah. But there, let's see, if I go to OSI, that's licenses and standards. If I go click on BSD3 clause. Yeah, there are some other websites that have a nice kind of listing of what you have to do in order to comply with the license. And they're usually pretty short, so you can kind of read through them. But yeah, I think MIT or BSD is good. Other questions?
I'm not sure I understand how this is just me not understanding things, how the test folder, like, lets you test the code without it, like, if you have the installation stuff above that as well?
The installation stuff's going to recursively go down through all of these folders. can I get back to your question in 1 second?
Yes.
So that's what the setup for Python is like. Alright, so from setup tools, import setup. Python has kind of a rocky history with the setup commands. Disuse tills is kind of getting phased out, and setup tools, which is a bit more closely tied to pip, is kind of the de facto standard now. So okay, setup takes in a dictionary, which we're going to enumerate here. So okay, first up is your package name. That is the name of your package. A version number. This is super important because we need a version number to make a package. Author or author's names. An email. And packages. So this is where we specify what Python packages, these are the Python folders that contain modules, we should go look at when we go to make the proper package. And we can see here that we specify package name and also package name.txt. So we told the setup.py, go into package name and then go into the folder tests and also package those Python files as well. There are some cute tools that I believe Setup Tools has where you can just say find packages and it'll recursively dive down all of your folders looking for dunder init.pys. And every folder that has that, it will then go and say, this is a Python package, we will include it in the package. Does that answer your question? So there are some scripts that you might put in there. You might also be able to say bin/star and just say everything that's in that directory is a script. You might hand it a URL, a license, some description, a really long description. This is usually maybe in Markdown, and install requirements. And this is where you specify your requirements for your package. You can get away with very little things in the setup.py. You don't need all of these things. You don't need the install requirements, you don't need the description. You probably just need the name of the version. You probably should include all these things though, because they'll be really helpful down the road. But this is kind of a standard setup.py. Note that many people put more things into the setup.py, especially for the C extension community. There's going to be a lot more things, not inside of here, but inside this actual chunk of code called setup.py. They're going to have a whole bunch of code saying, all right, and then you need to run the C compiler and the C++ compiler, and we need to run this, that, and the other thing. That might all be in here. One of the kind of annoying pieces about this, though, is that this is an arbitrary Python file. You can stuff whatever you would like into this, which is a little bit risky. They're usually fairly safe, and you can inspect them, so you can read them. But there's kind of a new format coming out where you can actually do all of these things from a configuration file, which is a little bit safer because you can parse it without having to, run it. Because you might just be interested in what are the requirements without actually saying, Python, install this thing that I don't know where it came from or what it does. And there are really good examples of this on various Python packaging tutorials, so kind of a copy-pastable version of this that you could run with. So how to submit packages with pip, or with pip to PyPI, which is the Python packaging index. So we install Twine. Twine is the PyPI's uploading tool. You can con install it, you can pip install it, no problems there. You tag the code in version control and change the version number. There are all sorts of tools for doing this. Anthony Skobats and I Anthony wrote one and I've contributed to something called Reverb, which is really cool. It's a little bit advanced, but it does really spectacular stuff for all these things. Once you've done those, run Python, setup.py, sdist, bdist wheel. So this is source distribution, and go make a binary distribution in the wheel format. There are also some shortcuts for this. And then once that's done, it will have produced a source distribution and a tarball that contains your binary code. You can then say twine upload your repository URL. Note that this is going to the testing. So this is just to make sure that it uploads properly and PyPI is happy and whatnot. And then finally you can say twine upload dist properly this time. So this is going to properly put your things onto PyPI. Note that PyPI has some naming issues sometimes. There are apparently limited. There might be unlimited names in the universe, but there might be limited popular names in the universe. So you need to check that your package doesn't conflict with an existing package on PyPI. That's, you just kind of search PyPI and see what the name of your thing is. We've gotten around this by adding Z's to things, like streams, but spelled with a Z. So that's PyPI. So I'm going to talk a little bit about Conda. Now, that was all kind of Python specific. This is less Python specific. So there's a tool called Conda build that you'll need to install. And of course, you can Conda install it. This needs to be done in your root Conda environment. So one of the restrictions of Conda, note that this isn't root as in root privileges. No sudo was used in the making of this Conda build. You can't run it inside a Conda environment. And the reason is that Conda doesn't allow you to access its own API inside a Conda environment because Conda doesn't live in that environment. It lives in the top level root Conda environment. It's kind of a weird little nitpick. So it uses its own format for specifying package metadata called a meta.yaml. This includes a lot of the same information that's in the setup.py, but it's a little bit more intricate because Conda does more things, like build binary things for C, where that's going to be very different than just installing a interpretable Python package. Now there's a really nice tool called Conda Skeleton. Conda Skeleton can go to PyPI or CRAN, and maybe CPAN, I'm not certain, which is the Perl packaging system. CRAN is the R packaging database. And you can tell it, I would like you to make a Conda recipe, also known as a meta.yaml, for my awesome package from whatever source. And it will do its absolute best to read whatever metadata was associated with that package and compose it into a meta.yaml. This is a lot nicer than trying to write one from scratch. You can then run Conda build past the meta.yaml, and it will build the Conda package. And then you can finally upload this to your personal Anaconda account, assuming that you made one. So Conda install Anaconda client, Anaconda login, Anaconda.upload. And the Conda build process will tell you where these files are on your file system. So that's Conda. So I've gone a full 37 slides without talking about Conda Forge, which I think is like a new record for me. Okay, so Conda Forge is a community-driven packaging ecosystem. Pretty much kind of one of the potential origin stories that one should take with a grain of salt was that, so pip existed for a while, but in the beginning, Python wasn't so great about handling binaries. It was a real tough time getting things like NumPy, SciPy. Of course, back in these days, might have been numeric, installed on your system. And that's if you were running Linux. Mostly because PyPI was predominantly a source distribution. It would gladly hand you the NumPy source code, but it was up to you to do all the crazy compiler stuff. So Conda came along after that, and this was right about the same time that Wheels started, so they're pretty close. And so the idea was that Conda wanted to distribute binaries rather than source, which pushed this problem of how do I compile the source code away from the users and back to the people who wrote the source code and made the packages, who are actually the people most likely to know how to do it properly. Go figure. And so that was great. And then Conda has channels, so you could upload packages to your channel, and that was wonderful. The downside of this is that it became kind of the wild, wild west of channels. Like, everyone had a channel. No one knew whether or not they compiled that channel compiled the code correctly and uploaded it. You had no idea what was in there. And there was certainly no one-stop shop for where to get all of your packages from. And so Conaforge came in to try to address this issue on a couple levels. So one is that Conaforge, packaging is not always easy for beginners, especially when you start to have really nasty C extensions or Fortran, things in there, like life gets a little bit sticky. And so we actually have packaging veterans as part of Conaforge Core and Conaforge State Recipe Reviewers that actually have done this for a while and kind of know all the nifty little tricks and what flags to use to get the extra debug messages so you can see what's going wrong to help out your packaging efforts. Also, most developers, even if they build the things correctly, they don't have the infrastructure to build on every single platform. To do this properly, you would need to have a Windows system, an OS X system, and a Linux system, potentially in all different flavors of 32 and 64 bits, in order to get the maximum amount of coverage needed for people to download your package. That is not sustainable. And so we actually automatically build on Windows, OS X, and Linux with ARM, also known as cell phones, and PowerPCs, which are popular with the supercomputing crowd coming soon. The way that we do this is that we use continuous integration. And I haven't talked about this too much, but continuous integration is a great way to run your tests. It also works out really nicely to build packages. Pretty much there's an external server. Every time you push stuff up to GitHub, the continuous integration server spins up and tries to run your tests. Or in our case, our tests are build the package and upload it, please. So this is really convenient because it's all automated. It forms a one-stop shop with 5,500 packages plus packages across many languages. We have at least 1,500 R packages, I think, currently, and a whole slew of Python. And we're really good about keeping up to date these days. This wasn't always the case, but we now have some automated tools for keeping everything up to date. So as new versions of software come out, we actually, within a couple hours, have those things ready to move. So okay, so how to submit packages to Conaforge? Conaforge is a little different. So one is fork this repository, Conaforge Stage Recipes on GitHub. Stage Recipes is kind of the gate to Conaforge. This is where people propose packages that they'd like to have made. Make a branch on your fork. You're going to want to download this and have a local copy on Git. Add a directory for your package. I will give an example of this, and you'll see what that means. Add a meta.yaml to your directory. There's an example one, so you can just copy paste that one and then just change all the names and version numbers of things. Or you can run from con to skeleton and copy it over. Commit it, push it up, and then open a pull request. At that point, we will then see that that exists, that your request exists, and once all the CIs pass, meaning that they could successfully build the package, and it passes review, it'll get merged. Once that's done, your code will be up, that package will be up on Conaforge. After that, an independent repository will be made under the Conaforge organization, where you will have commit rights to that package, so that you can update it, you can modify it, whatever you need to do, totally fine. One super important caveat, please, never modify the code in the Conaforge repo. Always make a branch on your fork and open a pull request. We build on every single branch on all of our repos in case you need to push multiple versions at once. For instance, if you're backporting something. So we really don't. Anything that you do on that will be automatically built, which could be really bad. Okay, so building packages, hands-on. All right, so I'm going to make a scrap directory and then move into that directory. And we're going to use conskeleton to build a recipe for streams. Specifically using this command, conskeleton pipeline streams. This is assuming that you have conda build installed already. If you don't, you should probably do that. All right, let's get ourselves in terminal. Let me pack them up. Okay, there's nobody in my directory. So, again, I kind of did this last night. Make sure that it all worked. All right, so it's found a bunch of versions. Nope, can't step away from putty. So it's going to use the latest because we didn't ask it for a specific version. It said that it's going to go download it from PyPI. Okay. It's thinking. It's going to think for a little while. It's going to try to read the metadata. Still thinking. Lots of thinking. Sure. So Conda skeleton is trying to go to PyPI, find an existing package on PyPI, maybe one of your dependencies. At which point, it then goes and grabs that code, copies it into a temporary directory, and tries to read through the PyPI metadata in such a way to then produce a conda meta.yaml, which I will show right now. So there's now a streams directory. If I look at the streams meta.yaml, that is what it looks like. So you can see here, we did some fancy things. Namely, this is called Jinja 2 templating. You don't have to have it. It's in the example as well. But pretty much you can replace this with your package's name and this with your package's version, and everything will work fine. Then inside this, so we have a package. It's got a name and a version. Good. We have source. So we need build needs a place to go get the source code from. So that's this thing. And we're including a checksum. So this is SHA-256. This is to make certain that what we think we're packaging is exactly what we're packaging. If these two didn't match up, that would mean something weird was happening. Either we pointed at the wrong thing, or there was a man-in-the-middle attack that someone was trying to force us to build an invalid package. Afterwards, there's a build section. So this is build number. This is just an extra it's not an actual version number, but it allows you to specify different builds. So if you messed up the build the first time, you could fix it and increment this number, and things should be good. And then this is the script that we run. So we say Python module pip install here, no dependencies, ignore install, no capture, and hyper verbose. And that's just our way of making certain that no deps makes certain that we get all the dependencies from Conda. If you couldn't get them from Conda, well, you probably should need to go build those first. Ignore install again does the same thing. No cache makes certain that we don't pull any PyPI cache information. And these are the requirements. These are the host and run requirements. Oops, you duplicated pip here. So the host requirements are what's needed to exist when we go run the build script. So for instance, we need pip because we said we need pip. We also need Python and sticks and tools and whatnot. And then the run are the runtime dependencies. So you don't need to have the host, well, no, you do need to have the host dependencies when you're running and installing Python packages. It's got a test section. The test section could include commands, say, run my test. This is how to run my test. We at least require an import test, and that just makes certain that we link to your package properly. And then there's an about section. And the about section has a URL, a license type, whatnot. We actually require you to provide a license family, some summary. And then, importantly, this is where you add yourself so that you are specified as the recipe maintainer for CondaForge. So that is the magic place to put your name, your GitHub ID, so that you get all the needed privileges. Sorry, that was a very, very long walk to answer your question. So now that we have this in hand, we can run Conda. We can finally build the package. We have the metadata. We have a link to where the data exists. We can go build it. Oh, I'm going to do that one later. So Conda build, path to the meta.yaml. So it's going and making an environment that has all the needed host dependencies in it. It's preparing this. Now it's going and doing its runtime dependencies, I think. And it built the package, or it got a package. It's now building it. These are the runtime dependencies. These are also the testing dependencies. Finally, we got an error. That's nice. So, when it tried to go and import something, it errored. There's no import, no module named NumPy. This makes a lot of sense, though. We didn't ask for NumPy. Like, we specifically gave, when we said these are our requirements, NumPy was not one of them. And the reason is that actually these modules are optional. So that's an optional dependency. So what we can do is remove the test that goes and points at that thing. So we can import streams. That will be good enough for me. Try this again. By the way, you don't have to do this, but it's fairly common to test your meta.yamls before putting the pull request up to CondaForge. Just because the CIs can be rather slow, so you don't want to have to wait 20 minutes to get back feedback saying, oh, we didn't put NumPy in the requirements, kind of thing. Although there are some times where there's no other options. If you're trying to build on an architecture you just don't have, there's nothing to be done but to just wail on the continuous integration services. Okay, so this built successfully. And if we scroll up a little bit, it will say this. It actually tells us exactly the command we need to run. Anaconda upload that thing. So you can just copy and paste that into your terminal, and it will upload it to your Anaconda account, assuming that you have logged in. That's kind of how to build a Conda package. All right. Oh, yeah, I should have put this up earlier. Yeah, hey, might need to remove those, as we did. And that's the way things go. You try to run Conda build, it works, great, or if it fails, you kind of see what the error messages are and try to debug it a little bit. And there's a little bit of back and forth. And again, if you really are running into problems packaging something, even if you know that it doesn't work, you can put it up onto Sage recipes as a pull request and say, all right, I know this isn't working, can someone help me out? And people will be able to say, oh, you're missing this thing, or whatnot. All right. So, to package things, first, make certain that your code is ready for packaging. This means tests, documentation, need to have a setup of Pi for Python projects. We talked about how to push packages up to PyPI and Anaconda using their command line utility, and how to push up recipes to CondaForge so that CondaForge could merge them to produce CondaForge packages. We finally solved the last little chunk of our catastrophes, namely, if we wanted to install something on our Boston machine, don't do it. Just tell them how to install it via Conda or PyPI and let them do it for themselves. The package manager will sort out all those problems, and then if they broke their machine, it's not your fault. You're not liable to fix it. Maybe. No, that's never how that happens. You're always liable to fix All right. So now I'm going to kind of talk about my perspective on this whole thing. So I'm a core developer for Carnivore. This is my GitHub handle. If anyone needs to find me on the internet, that's where I am. I mostly these days just keep things moving. I actually don't make that many packages. I kind of packaged all of my dependencies that weren't already on Carnivore, and I kind of haven't written that many new things that are outside of that stack. But I get a really interesting view of the entire ecosystem. How we interact with continuous integration systems. How we interact with GitHub. This one's particularly thorny. We might actually have maybe the most public repositories of any organization on GitHub at this point. Someone compared us to the Monty Python sketch, The Spanish Inquisition, because whenever we show up on a CI system, we almost automatically make the UIs break, because they're not ready for 5,000 repositories all trying to build. And then we also get to make some interesting decisions about how to build things so that everything's consistent. And when new low-level libraries come out, do we move to those new level libraries? How do we do that? And I find it really interesting. My kind of extremely broad mission statement is to take things that humans don't do well or don't like doing and handing them to computers. And building packages is definitely one of those things that actually fits in both of those two categories. So automating that, I find really fascinating. So currently Counterforge runs on 3 continuous integration services. Travis CI, which supports our OS X builds, AppFair, which builds Windows, and Circle CI for Linux. We'll be moving, I believe, AppFair and Circle CI builds over to Azure pipelines in the near future. They've been very generous in terms of giving us extra builds. This is one of our primary bottlenecks. It's just that we have so many packages that need to be built that we really queue up the servers quite high. By the numbers, we have over 5,522 GitHub repos with over 5,500 different code bases, over 1,000 contributors, 120,000 artifacts. So these are different versions or different dependency packages, which amounts to over 450 gigabytes worth of data sitting on anaconda.org. Anaconda Inc., the company, is very generous in terms of giving us free space. Over 40,000 pull requests issued. 10,000 of those came from a completely automated bot. So this is quite staggering to me, is that 1,000 contributors have produced 40,000 pull requests. We have a whole bunch of bots running around doing a ton of maintenance. Like I said before, it's a really cool problem space. It's got this kind of double effect where software engineers really like automating things. But now we're kind of automating things about software engineering, and it's like you let the software engineers loose, and they just start automating all the things. It's like, oh, I don't like that. Automate it. It's quite magical. So this is what it looks like. This is a picture of Condaforge. This is one of my baby pictures. So this is 5,000 packages in a graph. You can actually play with this. This was written using Bokeh on this website. Fair warning, this is 32 megabytes worth of JavaScript. It may or may not slow your browser down a little bit. And you can kind of see how all the things are interrelated here, especially if you look at the web version where you can click on the things and see who's who. This was produced by Justin Calamari, who was a summer student working with us as part of the Google Summer Code Project. He did some really awesome work. And this is all leads to dependencies. So kind of frontiers and kind of contours and packaging. So keeping everything up to date is really a challenge. Code is constantly being released. And as we add more packages, the code is getting released even faster because we just have that many more. So we have a bot called the Regro CF Automatic Bot. It was a collaboration between the Regro project and Conforge that scours the net every hour looking at all the source code to see if new versions have come out. And if those new versions have come out, issue a pull request saying there's a new version, we should build a new copy of this package with the new version. This seriously reduces the burden on maintainers. In the past, maintainers needed to actively go look as to whether or not that code had been updated. Usually, those maintainers are actually not associated with the projects that they maintain because you depended on some code that wasn't packaged yet, so you packaged it yourself for content launch. Now, they pretty much just hit the green button and make certain that the dependencies are correct. This is a real nasty thorn in our side because many times new versions might move the dependencies. You might add a dependency on scikit-learn or on bokeh or something that wasn't originally in the package. And now we need to say something about that so that we correctly satisfy all of the constraints. One of the things hopefully we'll do in the future is to implement some ways to automatically inspect for dependencies. There's a cool project called Depth Finder, where it will actually read your Python code and find every single import statement so that we can then go and try to say, well, here's what Depth Finder thinks all of your requirements are based off of everything that you imported ever. Does that match with what the package thinks are your dependencies? And that would also help reduce a lot of maintenance burden on this. Keeping everything compatible. So keeping everything compatible is also a nasty challenge. There are some packages that are just integral to the ecosystem. And they're the ones, they're the usual suspects. NumPy, SciPy, OpenBLOS, Python, all these things are super important to make certain that your environments are compatible internally. So when those packages are released, many downstream packages, potentially including yours if you link directly to NumPy, for instance, might need to be rebuilt so that everything is compatible. So the regrow autotick bot is also used here for some of this because it actually has access to that huge graph thing and can rebuild things in order properly. Rebuilding all the things. So recently we moved compilers. So originally we were on the GCC4 compiler toolchain, and we moved to GCC7. These are not compatible. If you tried to run the NumPy that was compiled with GCC7, with a SciPy running on GCC4, those things would break not just badly, but they would break in ways that aren't unintelligible. Like they would give you error messages that made no sense. And so we got a taste of this kind of rebuild the world setup where we moved C compilers. This is our progress bar, or this is the static copy of our progress bar. It's probably farther along now. There's a Coniforge status page, and this is at the top of it. And this maps all of the things that we're moving. So you can see that we have almost 2,000 packages that have been moved, 400 that are in PR, so we're waiting on some modifications to the package to make certain that they work. 555 that are waiting PR. We don't have everything go at once because otherwise we would swap the four CI systems. And 582 awaiting parents, meaning that because some upstream dependencies haven't been rebuilt yet, we can't rebuild those packages. Note that this rebuild is not just to change its C compilers to be compatible with the default Anaconda distribution, but also the release of Python 3.7 and the release of R 3.5.1. So we really did hit almost everything in the stack, except for pure Python packages. So instead of a hands-on section here, this is my call for devs. This is a really interesting problem space, and there's a lot of really cool people working on it, and we're really interested in getting more people involved. However that is, submitting pull requests into stage recipes, updating packages, maintaining packages, or if you're interested in the infrastructural side, working on the infrastructure. There's a bunch, not all of those repositories are packages. Some of them are actually the infrastructure that we use. How do we build on the CI? How do we check that the packages are properly formatted? How do we make sure that everything's being updated properly? We are very interested in having developers join us on these packages and this work, and I find it quite fascinating personally. Okay, so references and other resources. So I have borrowed heavily from my fellow Converge devs and colleagues, including SciPy's 2018 SciPy, The Sheer Joy of Packaging. This is a really great packaging tutorial. They do a lot more in-depth things that I didn't talk about here. Because they're more focused on the how to make packages side, and do great things like talk about how to make C packages for Conda, which, if that is a thing you need to do, that is very much a thing that you need to do. And so there are a bunch of great presenters on this. There's a YouTube video of this. I've stolen some of the stuff here. This is under a Creative Commons 2 license that we are also under. Marius Van Niekerk's PyData NYC 2015 talk for the numbers. And Felipe's talk, also from SciPy 2015, discussing Conda Forge, available here. SciPy 2018's The Sheer Joy of Packaging has some really great length. Like, the tutorials are not that long in terms of like scrollable web page, but they have some really great links for uploading things to PyPy and how to do PyPy things and examples and a whole discussion of Cookie Cutter that I didn't get into, but it's a software tool for automatically building that folder structure that we were talking about earlier that you might be interested in. And you should totally give that a look. A lot of hard effort went into that. All right, acknowledgement. A lot of the packaging work that we're doing is under the NSF VMref grant. Justin Calamari's work on the auto-ticking bot and Dependency Graph was part of a Google Summer of Code project. I would like to have lots and lots of thank yous for the Conda core dev team. They're really a spectacular group of people, really knowledgeable, really helpful, great mentors. My fellow members in the Conda Forge bot team, or we run the automation, or some of the automation tools for keeping the bot running and my sanity intact to whatever extent I have it left. Professor Billings, my advisor, the rest of our research group, who sometimes serve as guinea pigs for various new packages that I put out, and the entire Conda Forge contributor ecosystem for all the spectacular work they do. It really would not be possible without the 1,000-something people involved in the project. And with that, I'm happy to try to answer any questions that you might have. If you have packages that you'd like to try to build, I can try to help out with those. I can run a demo of building a package that I actually don't have on Conda Forge yet and uploading that to Conda Forge. If anyone thinks that would be particularly helpful, thank you all very much. Yeah. Sure.
First, as a developer, do you get paid by Conda, or is this a volunteer thing?
So this is an open source project. I am not paid by Anaconda or Conda Forge. So part of my work in terms of producing reproducible science is making certain that my libraries and source code are distributable and are not just distributed, but accessible. And to my mind, the way to do that is to package them and put them out for people to engage with. And as part of that, like we decided that it would be good to engage in the packaging system, not just to use the packaging system, but actually make it better. So no, I'm not currently paid by Conda Forge, but I mean, we have Google Summer Code for people who do want to make money.
Second, so I always thought that Conda was really Python based, and so you're telling me that there's R packages or other types of packages on there. So is the idea of Conda to just have all packages for all languages in one source? Because obviously Cran, for example, probably has a lot more for R.
Okay, so this is an important distinction. Conda itself is written in the Python language. It was a convenient language to write things in. However, the packages that Conda builds, installs, and manages can come from whatever source code you'd like. So we do support R. We support Lua, OCaml. If we don't, we support Go, I believe. Yes, we do support Go. And we're happy to take on more languages if you have a language that we don't support yet. I almost forgot to mention, there's also a kind of sister project to Conda Forge is something called BioConda. So they're also a GitHub-based organization that builds Conda packages from repositories, similar to how we do, but they're more focused on the bio side of the operation. And so they inherit a bunch of things from us, and a lot of people use both Conda Forge and BioConda simultaneously to do various things. But yeah.
So what kind of packages would go on BioConda versus
Oh man, that's a really nasty question. So that's a question that we actively hash out, and we have good communication between the two projects. So if you put something up to staged recipes that might be better on BioConda, some of the BioConda people that are actually serve on our board might say, hey, you might want this on the BioConda side as opposed to the Conda Forge side. But I think there's a lot of intermingling, and so some things it matters, some things less so.
other things that do matter? I just
So-
don't understand the distinction.
The main problem that we run into, the majority of the problems that we run into with BioConda is that someone submits a package to Conda Forge, which is independently packaged on BioConda already, that has an overlapping namespace with BioConda. So you make package XYZ, but XYZ is already on BioConda, at which point we need to modify the package name on Conda Forge so they don't conflict. But there might be a slightly different NumPy pinning for BioConda, but I'm not certain. I have to check. I mean, again, like I think that at that point, you might as well submit it to us, and worst come worst, we'll say, well, you might want to go to the other side. It also depends on how many packages you depend on. So, for instance, if you depend on a lot of packages that are in BioConda, but not in Conda Forge, probably better to send it to BioConda, because otherwise you're going to have to build all of those dependencies for Conda Forge.
That's one issue with Conda Forge, that all your dependencies need to be on Conda Forge, right?
Yes, but that is the same for BioConda. So BioConda, the restriction, it's a little bit different. So on BioConda, all of your dependencies must be on BioConda or Conda Forge or Anaconda defaults. So we also support a handful of packages from Anaconda defaults because building the GCC compiler from scratch is incredibly time consuming. Like, we will run out of time when our CI is consuming. So yeah, so to some extent it's just kind of play it by ear or ask. I think there are people that have strong opinions. I am one of those people, and my opinions are subject to something when I'm not on the microphone. Yeah, that's a break. So, other questions? Yeah.
I have a question about environments.
Sure.
So I was thinking about not creating a package, but if I have a certain number of scripts that I run for an analysis.
Yep.
One idea that was proposed in the previous lecture was creating a bash script file to run those Python programs one by one.
Sure.
Instead of doing it manually. But when I try to activate the environment source activate using a bash script, it doesn't activate the environment. Do you know why is that?
Yes, because source activate does some really janky bash things internally.
So it always has to be done manually before you do that.
There might be ways to do it externally, but I don't know them off the top of my head. Yeah.
I mean, I've done source activating on like bash scripts and like, within a cluster, like on the submit script.
Really?
Yeah.
I've had issues with that in the past. But okay.
Try to get
Yeah. I mean, I've done that and it works.
Okay. All right. Well, if anyone's interested, I will now attempt to do a high wire act. So I am going to package Caproto. Conda, skeleton, PyPI, Caproto. whole bunch of RCs. Now I'm also going to, while it's going, I have an open browser. I do have an open browser. I'm going to cheat. No, not Slack. Because someone else has already made a conda package for this. It's not on CondaForge. So I'm going to steal a lot of their package. That's still going. More than one terminal open at once. Yeah. Stage recipes. So I already have a copy of stage recipes. Git checkout master. Let's look at it this way. So that's a little more readable. All right. So you'll see inside of here there's a recipes directory. I could do, let's do git pull. So if I change directory into recipes, you see that there's an example here, so we can look at the example. And you can see that the example actually has a lot of comments in it to try to like help you along and describe what's going on and why. Actually, I'm going to do this from scratch. It'll be more fun that way. So I don't need this. All right, so git checkout -b create proto. Because I need to work from a branch, and I don't want to use master. Make dir create proto cp example. You can see that I've done this a couple times before. All right. So I've copied the example. So if I go and edit the example, not the example, sorry, the create proto. So, the name is definitely not simple JSON. By the way, this is a library used 0.2.2 at the NSLS, prototype library used at the NSLS2 for control of motors and a bunch of other things. All right, so I'm not going to get this from PyPI. I'm going to go get this from GitHub, because I can totally do that. You don't have to upload things to PyPI because maybe you don't want to. I don't. It's not a good habit, but it hasn't hurt me just yet. So we're going to use SHA-256, which I'm actually going to go steal from the conda build, or the conda skeleton. Can I do that? No, I can't do that. So let's go. And the first thing I need to go and change this, because it's definitely not simple JSON. It is called CA-Pro. Okay. And I can go to wget this, or curl if you prefer. And I can fill these in. I have a tool for doing this, but I thought I'd do it with my hand. And that's actually incorrect. This needs to be NSLS2 because that's where the org is. Yeah. Let's go find it then. So, sorry. I'm going to the GitHub web page. And I'm going to look at the releases. And yes, there's a, it's the V0.2.0. It's the little things that get you. So I can go here and put in a V. Now I've got it. And we run SHA-256 sum on the 0.7. So this is going to do a check. This is going to do a checksum on this tarball to make sure that it's the correct one. So this one. And that gets inserted in right here by where it says jump to 56. Well, not two. No, I only wanted one of them. Depending if Vim would cooperate. Great. And this needs to have a V in front of it. And that's not Caperto. That's SS2. Alright, so that's this section done. I'm going to use something called no-arch Python. This means that it's a pure Python package. It has no Python 2 versus Python 3 differences and no differences based off of operating system. It's really nice for us because this allows us to only build on Linux and it works on everybody, which seriously cuts down on our CI costs. Okay, the build number is 0. I don't need all those comments. So this is the new Python command. So Python pip install, like we saw before. I don't need a build section because that code does not compile any C stuff. So I don't need any compilers. I do need a host and a run. So Python and pip. Great. Now I need to actually go look for some more dependencies. And this is actually the reason why I'm not using the skeleton version, because if I actually go into here, it didn't catch any of them. I should talk about entry points. All right, actually I'm going to copy these. So entry points are scripts. That's how you specify scripts in Conda. Again, there's an exhaustive documentation for this on our website. But this means that you'll be able to run commands like proto get from the command line. But it didn't capture any of the dependencies, which was a little bit sad. So we're going to need to go do those ourselves. But that's okay. We have GitHub. So usually there is a requirements file, for instance. These are test requirements. Note here that Conda Skeleton didn't find anything because the extra requirements weren't really listed. So I'm going to list these extra requirements that are somewhere here. Okay. Netty faces, which I think is maybe a network interface code. NumPy. Trio. Trio is spelled differently. No, be sure. Oh, I should follow up on the do we get paid? Some of us actually do get paid. Sorry. Anaconda does, so maybe like 40% of our board, which is 17 people, work for Anaconda Inc. So, and I think they're paid. And I think Conda Forge is part of their mission. And other members of us get paid, not specifically work on Conda Forge, but as part of their open source work. So you won't start helping out with Conda Forge. Right. And so now we're just going to use some import tests. Save proto. The home is not this one. It's NSLC2. Proto. This is a reminder to do the licenses. You don't have to follow along with this. I assumed that I was going a bit quick to do. All right, so it's a BSD license, and maybe it's been packaged. Hopefully, I just any. Come on. Please. Headers. Damn it. They didn't package the license. I'm annoyed because that's something that we actually want. All right. This is a BSD license now. 36 is BSD, and this is a 3 clause. And it's in the license family of BSD. BD. It's that one. Maybe that's okay. And we need a description, so we can go take that from the README. Summary. And then I will blow away the description because right now you shouldn't do that, but I'm trying to do this quickly, so. And I will add myself. Great. So now we're going to write this down. Git add proto. Git commit. Add proto. Git remote dash v, because I forgot where I am. Git push dash u. Right. Proto. And if we go on to GitHub, just stage recipes. Time git. Okay, and if we refresh the page here, come on. Be a green button. Yeah, I'll just make this the old-fashioned way. So then we can make more. And now I have submitted a package to Common Core for packaging. And that's the whole bag. So, all right. Well, thank you all very much.